Well, today let us discuss about photoelectric effect. Okay, photoelectric effect. Now, what is photoelectric effect? When light with sufficient energy falls on some metals, electrons are emitted. Okay, so for example, say zinc metal. This is a zinc metal. This is zinc metal. Okay, say light falls on zinc metal. Light falls on zinc metal. So electrons will be emitted. Electrons will be emitted. Okay, but if you allow visible light to fall on zinc metal, no electron is emitted. Okay, visible light পড়িলে জিংকৰ পৰা ইলেক্ট্ৰন নোলাব. But if you allow UV light, UV, ultraviolet, if you allow UV light to fall on zinc metal, electrons are emitted. So we know visible UV, X-ray. You remember this? You remember the sequence? Okay. IR के visible or wavelength कम, wavelength decreases, और wavelength decreases माने wavelength decreases, that means energy increases. Okay, so you see visible UV, less wavelength means more energy. Okay, visible light less energy than UV. When visible light falls on zinc, no electron is emitted. But when UV light, more energy. When UV light falls, electrons are emitted. So when light with sufficient energy falls on zinc, falls on some metal, electrons are emitted. This is known as photoelectric effect. Okay. Now this photoelectric effect was studied by one scientist called Leonard. He studied photoelectric effect in detail. Okay. How he studied photoelectric effect? Say, let us assume like this. Say this is a glass tube. Okay. This is a glass tube. This is a glass tube. Okay. Glass tube. And this is highly evacuated glass tube. Okay. Now here this is a metal. Okay, this is the metal, and it is connected like this. Again, this is electrode, it is connected like this. Okay, and this is also connected. Simply we can represent like this. This is negative, positive, it is connected like this. Then there is emitter to measure current, and it is connected like this. Okay, so this is positive. Okay, this is positive, this is negative. So this is a beam of radiation. Beam of radiation is coming like this. The beam of radiation, it is coming and it is falling on the metal. So electrons are emitted. So electrons are moving from here to here. So electrons are moving, that means there is electric current. And this electric current is known as photoelectric current. Okay, this is the photoelectric current. Okay, so this is the assembly which Leonard used to study photoelectric effect. Now how he studied First, what Leonard did is that he used a radiation of definite frequency. Okay, definite frequency. Okay, then he increased the intensity of the radiation. Intensity. Say, suppose yellow bulb. Yellow bulb means 589 nanometer. Yellow light means 589 nanometer. Suppose, just assume this is a yellow light. So 589 nanometer wavelength. 589 nanometer means definite frequency. Now if you use one bulb, light will be less. If you use two bulbs, same yellow, frequency same, but light will be more. If you use three bulbs, same frequency, yellow, so still light will be more. That means intensity will be more. You increase the number of bulbs, intensity will be more. But since you are using the same color, so wavelength or frequency will be the same. So Leonard, what he did, he used a radiation with definite frequency, then he increased intensity. Increase intensity. And at the same time, he measured the corresponding photoelectric current. Okay, photoelectric current. So first say intensity was I1, and photoelectric current, say corresponding photoelectric current I1. Say one bulb, yellow light, one bulb, intensity I1, corresponding photoelectric current is I1. Then say two bulbs, same yellow light, intensity will be more and current will be something. Okay, again three bulbs, okay, and so on. Okay, then he plotted like this: photoelectric current versus intensity. Photoelectric current versus intensity. And he obtained a graph like this. This is the graph at frequency say nu1. Okay. So what we find here, as intensity increases, photoelectric current increases. Okay. Photoelectric current increases means number of electrons emitted increases. Okay. So as intensity increases, number of photoelectrons increases. Okay, so photoelectric current increases, that means number of electrons emitted. These are called photoelectrons. Number of photoelectrons emitted. So this was the first observation made by Leonard. Then he used radiation with another frequency, say nu2 frequency, and he did the same thing. Say this is with nu2, which is greater than nu1. Okay, he used another frequency, another frequency, and increase the intensity and measure the corresponding photoelectric currents. Again, the graph was like this. Again, what we see, as intensity increases, photoelectric current increases. That means number of photoelectrons emitted increases. So this was the first observation. Now, second thing what he did, normally you see, this is positive electrode. So electrons are coming and electrons are collected here. Electrons are collected here. So potential here, potential at this electrode is called the collector potential. Collector potential. Collector potential. Okay, potential at this electrode is called the collector potential. Normally it is positive. It is positive. Now what Leonard did is that he decreased the positive potential here. Positive potential to komai nise. Komai ni negative potential bodhai guise. He increased negative potential here. Okay? And simultaneously he measured photoelectric current. Okay? So collector potential, let me write it like this, Cp, collector potential. Say when collector potential is, say, let me write it, say -1 volt, just assume -1 volt, photoelectric current say I dash. Okay? Say -2 volt, photoelectric current is say I double dash, and so on. So on. Then again he plotted this graph. Photoelectric current versus collector potential. Now this is a -1, so negative value increasing. This way. Negative value increasing, say -1, -2, -3, -4, like that. Okay? Normally how we draw graph? This is positive, 1, 2, 3, 4, like this. But here what we are doing, this is say -1, -2, -3, negative value increasing. Okay? Negative value increasing. So what he observed? He observed that, so photoelectric current decreases like this, and at a certain negative potential, photoelectric current becomes 0. So this is a -V0. At this potential, photoelectric current becomes 0. Okay? That means at this potential, no photoelectron is emitted. Now here you see, say this is the metal. Light falls on the metal. Okay? So electrons are coming out. Now it is not that all the electrons will have the same kinetic energy. Gutebur electronor kinetic energy eke nathake. Kisuman electronor kinetic energy besi, kisumanor kom, like that. Okay? Not all the electrons have the same kinetic energy. Some will have more kinetic energy, some other will have less kinetic energy. Okay? Now, when you increase negative potential here, then electrons with less kinetic energy will be stopped. I mean negative potential disu. Tamne electron ahibo nwaribo. Okay? Gotike jetia negative potential kom thake, tetia kunbur electron stop hobo? Electrons having the least kinetic energy. Tarpor negative potential to बढ़ाই গৈছো. Na? Kun bilak electron stop hobo? Jar kinetic energy besi ase. Aru ekebare ekebare lastot at minus v naught, which electrons will be stopped? The electron having the maximum kinetic energy. Okay, so at this potential, the electron with maximum kinetic energy will be stopped. So stopping potential, let me write like this: stopping potential, this potential v naught, this is minus v naught, this is called the stopping potential. Stopping potential minus v naught. Okay, so this stopping potential is a measure of the maximum kinetic energy. Stopping potential is a measure of the maximum kinetic energy of the photoelectron. ঠিক আছে নে? কারণ আমার লাস্টত কোনটো ইলেক্ট্রন স্টপ হ'ব, যেটো ইলেক্ট্রনৰ কাইনেটিক এনার্জি ম্যাক্সিমাম। গতিকে স্টপিং পটেনশিয়াল ইজ এ মেজার অফ দি ম্যাক্সিমাম কাইনেটিক এনার্জি অফ দি photoelectron. Okay, so this graph is obtained with frequency say nu 1. Okay, nu 1, and intensity I1, when intensity of the radiation is I1. Okay, because what he did, number 2, what Leonard did, he kept intensity and frequency constant. Leonard kept intensity and frequency constant and measured the stopping potential. Okay, measured the stopping potential. So frequency, intensity constant, and stopping potential is this much. Next, what he did, he again, now he increased the intensity. He increased the intensity. Frequency is same, intensity is I2, and I2 is greater than I1. Okay, intensity is more, so photoelectric current is more. Okay, intensity যেটা বেশি হ'ব, photoelectric current বেশি হ'ব। গতিকে ইন্টেন্সিটিটো বঢ়াই দি তেনেকে চাইছে আৰু নেগেটিভ পটেনশিয়েল দি গৈছে, photoelectric current measure কৰিছে। Now what we find here, the stopping potential remains the same. The stopping potential remains the same whatever the intensity of the radiation may be. That means stopping potential does not depend on the intensity of radiation. And stopping potential means maximum kinetic energy. So we can say that kinetic energy of photoelectron is independent of intensity of radiation. Okay, so kinetic energy of photoelectron is independent of the intensity of radiation. Karon stopping potential eke ase. Okay, so this is the second observation. What is the first observation? As intensity increases, number of photoelectron increases. That is the first observation, and this is the second observation. Third, what he did, Leonard, Now what he did, he measured, he varied frequency and measured the corresponding stopping potentials. এইবাৰ কি কৰিছে, ফ্ৰিকুৱেন্সিটো ভেৰি কৰিছে, ফ্ৰিকুৱেন্সি ভেৰি কৰি ষ্টপিং পটেনচিয়েল মেজাৰ কৰিছে। ষ্টপিং পটেনচিয়েল কেনেকৈ মেজাৰ কৰিব, নিগেটিভ পটেনচিয়েল বঢ়াই যাব, নিগেটিভ পটেনচিয়েল বঢ়াই গৈ যিটো পটেনচিয়েলত ফটোইলেক্ট্ৰিক কাৰেণ্ট 0 হ'ব, দ্যাট ইজ দি ষ্টপিং পটেনচিয়েল। আৰু এইবাৰ গ্ৰাফডাল কেনেকুৱা পাইছে, now stopping potential, this is stopping potential and frequency. Now the graph is like this. Okay, this is the frequency nu naught. This is the frequency nu naught, which is called the threshold frequency. Nu naught. Okay, that means now what we can observe here, so below threshold frequency, no photoelectron is emitted, but above threshold frequency, okay, above threshold frequency, what happens, as frequency increases, stopping potential increases. That means above threshold frequency, kinetic energy of the photoelectron increases as frequency increases. That means above threshold frequency, kinetic energy of photoelectron, let me write it like this, kinetic energy of photoelectron is proportional to frequency of radiation. Okay, so these are the three results observed by Leonard. Okay, these are the three results observed by Leonard. Now classical physics cannot explain these three results. Why classical physics cannot explain these three results? That means failure of classical physics or inadequacy of classical physics. Okay, classical physics. Now, why classical physics cannot explain these three results? Now, number one is, according to classical physics, light is wave. Classical physics, light is wave. Okay, and energy of wave is proportional to intensity. Okay, energy is proportional to intensity. So what we get, as we increase intensity, okay, so this is a metal, this is the metal, okay, and these are the electrons, So according to classical physics, as we increase the intensity of the radiation, then what happens, the electron will get more energy. because energy is proportional to intensity. So electrons are coming out. Why? Because electrons are getting energy from the radiation. Okay, electrons are coming out. Why? Because electrons are getting energy from the radiation. So according to classical physics, energy is proportional to intensity. That means if we increase the intensity, the electron should get more energy. So kinetic energy of the electron should be more. Okay. So according to classical physics, kinetic energy of electron, photoelectron, should depend on intensity. But what we find here, but experimentally what we find? So experimentally we find that kinetic energy does not depend on the intensity. Okay, so that is one drawback. Second point is that since energy is proportional to intensity, there should not be any, according to classical physics, there should not be any threshold frequency. Why? Once again, because electrons are getting energy from radiation. More intensity means more energy. Okay, so there should not be any threshold frequency. And what is threshold frequency? It is the frequency below which no electron is emitted. Okay, so according to classical physics, electron should be emitted at any frequency. Electron should be emitted at any frequency provided the light is sufficiently intense. Okay, according to classical physics, electrons should be emitted at any frequency provided the light is sufficiently intense. Okay, but practically what we find? We find that there is threshold frequency. Experiment kori ami ki paisu? Je ami etu paisue je threshold frequency ase below which no electron is emitted whatever the intensity of radiation may be. Below threshold frequency, no photoelectron is emitted whatever the intensity of the radiation may be. Okay, so you see the discrepancy. The classical physics or mote threshold frequency boli ekku thakibo nalage, kintu practically ami ki paisu je threshold frequency ase below which no photoelectron is emitted whatever the intensity of the radiation may be. Third aru eta kotha ase ki, since light is wave, so electrons should be emitted from the metal after some time from irradiation. Tane light porar kisu homoy pisothe electron olabo lage. Then there should be, according to classical physics, there should be time lag. There should be time lag for emission of electrons. Tane light porar kisu homoy pisothe electron emit hobo lage, since light consists of waves. Okay, kintu practically there is no time lag. Practically there is no appreciable time lag. So these are the discrepancies of classical physics. That means classical physics cannot explain the results of photoelectric effect. Then Einstein in 1905, he explained photoelectric effect using Planck's quantum theory. Okay, Einstein explained photoelectric effect using Planck's quantum theory in 1905. So, but there is some little difference between Planck's idea and Einstein's idea. There is some difference between Planck's idea and Einstein's idea. What is the difference? Planck assumed that light travels as wave. Planck assumed that light travels as wave, but it is absorbed or emitted as quanta. Okay? প্লাংকে কি ভাবিছিল যে লাইট আহিছে বা গৈছে, কেনেকৈ আহিছে বা গৈছে, ৱেভ হিচাপে আহিছে বা গৈছে, কিন্তু এবজৰ্ব বা এমিট কেনেকৈ হৈছে, ইন কোৱান্টা. কিন্তু আইনষ্টাইনে ভাবিছে যে লাইটটো কোৱান্টা হিচাপে আহিছেও, কোৱান্টা হিচাপে গৈছে. লাইট ইজ কামিং ইন কোৱান্টা, এবজৰ্বড অৰ এমিটেড ইন কোৱান্টা অল. গতিকে আইনষ্টাইনে ভাবিছে যে লাইটটো কোৱান্টাম হিচাপে আহিছেও, গৈছেও, আৰু এবজৰ্বো হৈছে, এমিটো হৈছে. লেটাৰ দিছ কোৱান্টাম মিনছ এমাউণ্ট অফ এনাৰ্জি. কোৱান্টাম মিনছ এমাউণ্ট অফ এনাৰ্জি, পেকেট অফ এনাৰ্জি. Later, this quantum was called as photon. Plancke jitu quantum buli goisil, pisot hetu photon buli koa hoise. Photon mane particles. It is a particle concept. Okay, you can think that photons are the atoms of light. You can think like that. The hydrogen, it has atoms. Oxygen, it has atoms. Similarly, light, it has atoms. And atoms of light are photons. You can think like this. Okay. So photon is a particle concept. Okay. So Einstein ki koise? What does Einstein say? So this is the electron in the metal and light is coming. That means quanta is coming. So the electron in the metal absorbs this quanta. Electron in the metal absorbs this quanta. So how much energy the electron gets? H nu. So from the photon, how much energy? From the quanta or photon, how much energy the electron gets? H nu, because the electron absorbs this much energy. Okay. Now the electron is bound to the metal, bound to the nucleus. Electron to nucleus logot bind hoi ase. Electron to jodi ahibo lage, ki hobo lagibo? First, this attraction must be broken. Okay. That means sum of this energy, how much energy the electron gets? H nu. And some of this energy will be spent in breaking this attractive force. Say W is the energy needed for breaking this attractive force. Now how much energy remains? This is the energy remaining energy, H nu minus W. Since energy cannot be created nor it can be destroyed, so this is the maximum kinetic energy. This is the maximum kinetic energy of the photoelectron. And this is known as Einstein's equation of photoelectric effect. And W is called the work function of the metal. বেলেগ বেলেগ মেটেলৰ ক্ষেত্ৰত ইয়াৰ ভ্যালুটো বেলেগ বেলেগ হ'ব ৱৰ্ক ফাংচন অফ দি মেটেল ওকে আৰু at threshold frequency what happens at threshold frequency say nu naught what happens kinetic energy of the electron is 0 at threshold frequency what happens kinetic energy of the photoelectron is 0 okay that means kinetic energy of the photoelectron is 0 so we can write like this nu equal to h nu naught minus w so kinetic energy of the photoelectron is 0 so from here w equal to h nu naught so we can write this equation as h nu minus h nu naught half mv square we can write like this okay so this is Einstein's explanation to photoelectric effect okay so let us see one or two problems let us see that okay okay so question you see the question problem the work function of chromium is 4.4 ev calculate the energy of the electron emitted when it is irradiated with radiation of 200 nanometer what is the stopping potential so this is the question very simple one very simple everything is getting given so work function is given w is given 4.4 ev electron volt converted to SI 4.4 into 1.6 into 10 to the power minus 19 joule okay joule then what is the wavelength is 200 nanometer this is equal to 2 into 10 to the power 11 meter 2 into 10 to the power 11 meter so simple use this equation so h nu minus w equal to half mv max square so here you have to find out kinetic energy means it is maximum kinetic energy so half mv square you can solve this no problem half mv max square equal to hc by lambda minus w so 6.6 h 10 to the power minus 34 joule second unit of h joule second c equal to 3 into 10 to the power 8 meter per second and lambda equal to 2 into 10 to the power 11 meter minus this 4.4 into 1.6 into 10 to the power minus 19 joule. Okay, so you just simplify this, and you will get the answer. Okay, so you can solve like this. Next, let us discuss about Compton effect. Okay, let us discuss about Compton effect. Compton effect. Compton effect. Now, what is Compton effect? Compton effect is that, say, it is related to X-rays. Okay, so you allow X-ray. You allow X-ray to fall on a target. This is target, and generally it is carbon block. When X-ray strikes carbon block, so X-ray will be scattered in every direction. X-ray will be scattered in every direction, and this scattered X-ray is observed. In Compton effect, this scattered X-ray is observed. Okay, and it is observed that this scattered X-ray has different wavelengths. This is a monochromatic X-ray. Monochromatic X-ray means having a definite wavelength. Okay, definite wavelength. So suppose it has wavelength this and frequency this. Wavelength this, frequency this. Now scattered radiation say wavelength. Scattered radiation wavelength say lambda dash, frequency nu dash. Okay. Now there is a different wavelength. In this scattered radiation, and that different wavelength. So different wavelength means this difference del lambda equal to lambda dash minus lambda. Okay. Now this difference between scattered wavelength and incident wavelength. So this difference depends on the angle at which it is observed. Okay, so let me draw it like this. Say this is a X-ray. Here X-ray is produced. Okay, X-ray is produced. X-ray is coming out in all possible direction. Now there is a collimator. This is called collimator. It will allow a definite beam of X-ray. This is called collimator. Okay, it will allow a beam of X-ray to pass through. These X-rays will not be allowed to pass through. Okay, this is the source of X-ray, collimator. Then this is the carbon block. Okay, this is the carbon block. This is the carbon block. And say this is the, if the X-ray is not scattered, then it will follow this path. Okay, it will follow this path. But scattering will be there. Say this is the angle. This is the angle at which X-ray is scattered. Okay, this is the unscattered X-ray. And this is the scattered X-ray. Now scattered X-ray is monitored. It is monitored with instrument called spectrometer. This is the spectrometer. Okay, spectrometer. The spectrometer monitors, observe the scattered X-ray, and it can be moved. It can be moved in a circular path. It can be moved in a circular path, so that this scattered X-ray can be measured at any angle. At any angle, scattered radiation, scattered X-ray can be measured at any angle. Okay, মানে স্কেটাৰ্ড ৰেডিয়েশ্যনটো চোৱাৰ কাৰণে যিকোনো এংগলত চোৱাৰ কাৰণে স্কেটাৰ্ড ৰেডিয়েশ্যনটো যিকোনো এংগলত চোৱাৰ কাৰণে দিছ স্পেক্ট্ৰমিটাৰ কেন বি মুভড লাইক দিছ, okay. So this is the part of the spectrometer. গতিকে এইটো এনেকুৱা কিয় কৰিছে, কিয় ঘূৰাই দিছে, যাতে আমি যিকোনো এংগলত স্কেটাৰ্ড ৰেডিয়েশ্যনটো চাব পাৰোঁ। And what was the result? It is found that del lambda depends on the angle, whether we have measured at this angle or at this angle or at this angle, it depends on that. So result is like this. Result of the experiment is like this. Suppose this is the suppose this is the wavelength of the incident radiation. Okay, this is the wavelength of the incident radiation. This is the wavelength. Okay, wavelength of the incident radiation. Now when theta is 0 means we are observing the scattered radiation along this line. Spectrometer is here. Okay, theta is 0. When theta is 0, it is found that del lambda is also 0. There is no difference between scattered radiation wavelength and incident radiation wavelength. There is no difference between these two, same. So del lambda becomes 0. But when, say, you see, suppose now say this is the incident radiation. And say angle is say 45 degree. Theta is say 45 degree. We have measured the scattered radiation at 45 degree with respect to the incident radiation. Okay, 45 degree. Then del lambda, this is the value of del lambda. There is difference. This is the incident radiation. Okay, del lambda. This is del lambda, here del lambda. Along this axis del lambda. So there is definite value. Okay. Similarly, if we say measure at okay, this is del lambda. Now this is say at when theta equal to 90 degree. This is the value of del lambda. So you see, del lambda depends on the angle. So as the angle increases, del lambda also increases. So this is the result of Compton effect. Now, according to classical physics, we should observe scattered radiation at any angle. It should not depend on angle. According to classical physics, del lambda should not depend on angle. But practically what we find, it depends on the angle. And value of del lambda increases by a definite amount as theta increases. So this result cannot be explained by using classical physics. So Compton himself explained this observation. How he explained this? Compton kenake explain korise? How he explained this? Teo prothomote thoi lise, say this is the photon. X-ray, this is the X-ray photon. This is the X-ray photon. It is coming, X-ray photon is coming, and it is hitting the electron. It is hitting the electron. This is the electron in the carbon block. Electron. This is the electron in the carbon block. This is the photon with energy h nu. Okay. Just like coins and striker in the carom board. Carom board etu jeniba striker, etu jeniba guti, na. Tarpsot ki hol, as a result of collision, this is elastic collision. Elastic collision between photon and electron in the carbon block. Okay. Then what happens? This is the original part or unmodified part. This is the original part or unmodified part. Unmodified or original part. Okay, this is the part. Now say after collision, say the photon moves in this direction, say photon. Say scattered photon h nu dash. Scattered photon. And this is the angle, say theta. This is the angle theta. So after collision, this striker moves in this direction. Okay, photon moves in this direction. This is the energy of this scattered photon. And say electron moves in this direction. Say electron moves in this direction. This electron is also called a recoil electron. What is recoil? I will tell you later. Recoil electron. Okay, recoil electron. And this angle is say phi. This angle is say phi. So Compton considered this to be collision between two particles. What type of collision? Elastic collision. He considered this. Now say energy of the photon before collision. Energy of the photon. Energy of the photon before collision. Before collision equal to h nu. And momentum of the photon. Momentum of the photon before collision, that is equal to h nu by c. H nu by c. Okay. Similarly, say energy of the electron. Energy of the electron before collision. Before collision, say this is a m naught c square. M naught c square. Okay. And energy of the electron after collision equal to say mc square. Again, energy of the photon after collision say h nu dash, and momentum of the photon after collision h nu dash by c. Okay, so what is the energy of the photon before collision? H nu. After collision, what is the energy? After collision, what is the energy? H nu dash. So what is the energy change of the photon? Energy change of the photon is h nu minus h nu dash. Okay, this is the energy change of the photon, and this much energy is received by the electron. This much energy is received by the electron. So what we get? we get this m naught c square. Okay, this is the energy received by the electron, mc square minus m naught c square. Okay, and this is the energy lost by the photon, so they must be equal. Energy lost by the photon is equal to energy gained by the electron. So this is a number one equation. This is a number one equation. Okay, but here you see we are talking about very high velocity of light, very high velocity. We are talking about very high velocity of electron, very high velocity of electron. So we are to consider as velocity changes, mass also changes. So we have to consider relativistic mass. We have to consider relativistic mass. What is relativistic mass? Say m. This is the mass when the electron is moving. This is equal to m naught. This is called the rest mass when it is not moving. This is equal to 1 minus v square by c square. This is root over d. This is root over v square by c square. So this is a relativistic mass, or we can write it like this: momentum. This is equal to m naught v root over 1 minus v square by c square. V is the velocity. V is the velocity with which the electron is moving. So you see, this is the velocity of light. As velocity changes, mass also changes. This is the rest mass when it is not moving. Okay, so we have to consider this. This is the equation number 2. Equation number 2. Now momentum is a vector quantity. Momentum is a vector quantity. Say, since we are considering elastic collision, so momentum must be conserved. Okay, since we are considering elastic collision, so momentum must be conserved. Momentum is conserved. That means x component and y component. So this is the direction. This is a x direction. This is y direction. Okay, so component of momentum along x direction, component of momentum along y direction, that must also be conserved. Okay, due to conservation of momentum, what we get now? What is the x component of momentum here? X component of momentum of photon. What will be this? What is the momentum? Momentum is h nu by c. So x component is this only, h nu by c. So x component is h nu by c, x component of momentum. Okay, and what is the x component here? What is the x component here? Okay, change in momentum, change in x component of momentum of the scattered. Okay, change in, okay, x component of momentum of the scattered electron, x component. So this will be h nu dash by c cos theta, x component of momentum. So h nu dash by c cos theta. Okay, cos theta. So what is this change in momentum? Change in x component of momentum is this. And this much momentum is gained by the electron. This much momentum is gained by the electron. So what is the x component of momentum? What is the x component of momentum of the electron? x component of momentum of the electron is, this is mass of the electron is this, m velocity is this, so mv, this is mv, this is mv, so x component of momentum will be mv cos phi, so this will be equal to mv cos phi, okay, mv cos phi. Now if we replace by relativistic mass, then this will be m naught v root over 1 minus v square by c square, v square by c square cos phi, v square by c square cos phi, okay. So this is the equation number 3, okay, this is equation number 3. Next, say y component, y component of momentum. So what is the y component of momentum of the photon here? So y component of momentum will be 0, okay. What will be the y component of momentum here? H nu dash by c sine theta. If we consider this direction sine theta, it is minus theta, this direction minus theta, this direction plus, this direction plus, this direction minus, cos of minus theta equal to cos theta, sine of minus theta equal to minus sine theta. So this is 0 minus h nu dash by c sine theta, okay, sine theta equal to, again this will be mv sine phi, mv sine phi, and this is equal to m naught v by root over 1 minus v square by c square sine phi, okay. This is the equation number 4, equation number 4. So we are getting these equations, okay, we are getting these equations. Now this will be, of course, this minus plus, this will be, so now we have to do some calculations, and after doing some we are getting the equations and we have to do some calculations. Now how to do the calculation? So one thing is that we can take the square of 3, take the square of 4 and add, okay. Say 3 square plus 4 square n, okay. What we get then? H square nu square by c square, okay, c square, then what is this? This a minus b whole square, a minus b whole square, so a square plus b square minus 2ab, using that formula. So this c square plus h square nu dash square c square cos square theta minus 2 h square nu dash by c square cos theta, okay. So a minus b whole square, okay, then plus this square, h square nu dash square plus h square nu dash square c square sine square theta Okay, sine square theta, sine square theta, then this is equal to m naught square v square 1 minus v square by c square. Square, we are squaring, and if we add this, we will get cos square theta plus sine square theta. We will get this. Okay, just simplifying. Okay, then we can simplify this also, or we get h square nu square by c square plus so h square nu dash square c square cos square theta, h square nu dash square c square sine square theta. So we can take this common. So then cos square theta plus sine square theta 1. So this will be h square nu dash square c square minus 2 h square nu dash c square cos theta. Cos theta is equal to m naught square v square 1 minus v square by c square. So we are getting this equation. Okay, we are getting this equation, or we can write like this. We can write like this. Say h square, we can take h square by c square common, so that we get nu square plus nu dash square minus 2 nu dash cos theta equal to m naught square v square 1 minus v square by c square. So this is the equation number 5. Okay, this is the equation number 5. So we are getting another equation number 5. Equation number 5. Then say from equation 1. From equation 1, what we can write? From equation 1. From equation 1, we can write like this: h nu minus h nu dash plus m naught c square equal to m c square. We can write like this. Now if we square this, so this is the a, and this is the b. So a plus b whole square. Okay, so this will be h nu minus h nu dash a square plus m naught square c to the power 4 b square plus 2 h nu minus h nu dash m naught c square equal to m square c to the power 4. M square c to the power 4. Okay, just squaring. Then we can or we can write like this. I can take h common, so nu minus nu dash whole square. So this will be nu square plus nu dash square minus 2 nu dash. Okay, then plus 2 again h nu dash m naught c square equal to m square c to the power 4 minus m naught square c to the power 4. M naught square c to the power 4. Okay, now we can divide by c square. C square, so that we will get h square by c square nu square plus nu dash square minus 2 nu dash plus dividing by c square, so which nu minus nu dash m naught, this is m naught, equal to m square c square minus m naught square c square. Okay, and this again for m square, what we can write? We can write m naught square 1 minus v square by c square minus m naught square c square. Okay, we can write this, or this is equal to 1 minus v square by c square. This is equal to m naught square c square. Okay, then this minus m naught square c square plus m naught square v square, so this will be cancelled, so we get this. We get this. Okay, so or h square c square nu square plus nu dash square minus 2 nu dash plus 2h nu dash m naught equal to m naught square v square 1 minus v square by c square. Okay, this. So this is the equation number 6. This is the equation number 6. Okay, so we are getting two equations. One equation is this, equation 5, and the other equation is this, equation 6. Now say equation 6 minus 5. 6 minus 5. Okay, 6 minus 5, so what will cancel out? 6 minus 5, let me write this, 6 h square c square nu square nu dash square minus 2 nu dash 2h nu minus nu dash m naught, then minus h square c square nu square plus nu dash square minus 2 nu dash cos theta. Okay, and that will be equal to 0, because right hand side is same, so this will be 0. Then we can take h square or h square c square, so nu square nu dash square minus 2 nu dash. Okay, then minus nu square, so nu square minus nu dash square, then this will be plus 2 nu dash cos theta plus 2h nu dash m naught. This is 0. Okay, this is 0. Now here this cancels, so or h square c square, then what we can do? We can take 2 nu dash common, and then this will be minus 1 plus cos theta, equal to minus 2h nu minus nu dash m naught. Now this will cancel, or nu minus nu dash. Okay, nu minus nu dash to m naught equal to h by c square, to nu dash into 1 minus cos theta. Okay, just reversing 1 minus cos theta, we will get this. Or nu minus nu dash, that is equal to h by 2 cancels, h by m naught c square, nu dash 1 minus cos theta. Now dividing both sides by nu dash, what do we get? 1 by nu dash minus 1 by nu equal to h by m naught c square 1 minus cos theta. Okay, or just bring one c here, c by nu dash minus c by nu h by m naught c 1 minus cos theta, and this is nothing but c by nu equal to lambda, c by nu equal to lambda, so lambda dash minus lambda equal to h by m naught c 1 minus cos theta. So this is the equation, and this is equal to, of course, this is equal to del lambda. So you see, so what is the drawback of classical physics? Physics is that it cannot explain why del lambda depends on the angle. Now from this explanation we can say why del lambda depends on theta, because in the expression we have got theta. Okay, so this is Compton's explanation regarding Compton effect. Okay, besides you see that del lambda does not depend on the wavelength of the radiation. There is no expression for wavelength. Del lambda does not depend on the wavelength of the radiation. So del lambda is independent of wavelength of the radiation. Further, it depends on the angle at which scattered radiation is observed. Now we can solve here one or two problems. Let me see. Well, let me see one problem. Say a beam of X-ray is scattered by loosely bound electrons at 45 degree to the direction of the incident beam. The wavelength of the scattered radiation is 0.22 angstrom. Calculate wavelength of the incident radiation. So here you see everything is given. Okay, everything is given. Simple, once again, very simple problem. So theta is given 45 degree. Then lambda dash is given 0.22 angstrom. That you may convert into SI. You may convert. Then our relation is this, and you have to find out wavelength of the incident radiation. You have to find out this. So very simple. So lambda dash minus lambda equal to h by m naught c 1 minus cos theta. Okay, so lambda will be equal to lambda dash minus h by m naught c 1 minus cos theta. Okay, and lambda dash is given 0.22 into 10 to the power minus 10 meter, h 6.6 into 10 to the power minus 34 joule second, m naught 9.1 10 to the power minus 31 kg, c 3 into 10 to the power 8 meter per second, and 1 minus cos 45 1 by root 2. Okay, is it 1 by root 2 sin 45? Okay. So just simplify and you will get the answer. So thank you. Next let us see what we can discuss.